There you go.
Okay.
All right.
Cool.
All right. Take it away.
All right. Thank you for the introduction, Matthew. And thank you to you and all the other co-organizers for this fantastic symposium. I feel very fortunate to be able to present my work here. So this work today is obviously in collaboration with one of my principal collaborators, is Matthew himself, the Army Corps of Engineers. There's also Peter Rivera Cassius at the Army Corps of Engineers, then Dr. Emma Ferraccioni at the University of Genoa, and Professor Mario Putti at the University of Padova. And quickly again, my name is Sourav Dutta. I'm a postdoc at the Army Corps of Engineers. Today I'm going to talk about our efforts at looking at data-driven or non-intrusive reduced order models for applications in environmental hydrodynamics that are of importance to the Army Corps of Engineers. And in particular, we'll be looking at an ML-based method called neural ordinary differential equations, and try to also compare it with some existing classical methodologies. A quick comment before we move on is, I don't know if you can hear, but obviously my dog seems to disagree with some of my choices of reduced order modeling methods. So time and time again, he might stage a protest outside. So sorry for the distraction. Today, since morning, thanks to the wonderful talk by Professor Hesteven, we have looked at different ways in which reduced order modeling, especially non-intrusive reduced order modeling, can help accelerate as well as augment our predictions based on our high fidelity solvers. So instead of going into the use of reduced order models, I'll talk quickly about the framework that we have been exploring for implementing these reduced order models. So if we have a high fidelity numerical solver as shown here, which produces system snapshots, then the first step is to extract or identify a low dimensional representation of the system using a latent space, or using a linear projection method like POD, proper orthogonal decomposition, which obviously guarantees some sort of optimality in the least square sense. The basis vectors are orthogonal, and they're also arranged according to the energy content. On the other hand, we can also go with nonlinear embedding methods from deep learning like autoencoders, which again have been shown to be much more efficient in convection dominated problems in some cases. So now once we have this lower dimensional representation in terms of these expansion coefficients Z0 to Zm, we can use various different methods to represent the dynamics in this latent space. We can use radial basis function interpolation, which is a classical method. We can use a Bayesian framework called Gaussian process regression, which produces a probability distribution of functions that can regress on the data. Or we can use the machine learning based neural ordinary differential equations framework, which I'll be talking a little bit more. And then using this reduced order model that we generate using one of these frameworks, we can now do predictions, again in the low dimensional space, and then reconstruct full order solutions, either using Galerkin projection or a decoder. Alternatively, there is also a method called dynamic mode decomposition, which looks at finite truncated representations of the Koopman operator to represent your original system in the space of Koopman nodes, and then model the dynamics, which is essentially shown to be very powerful for transient problems, which is what we'll be looking at today. So a quick overview of our previous work on this. We initially started by using the radial basis function method as our reduced order modeling framework. So if we have a semi-discrete dynamical system represented like this on the top here, then it has let's say linear terms as well as nonlinear terms. Then we can use proper orthogonal decomposition to find our reduced basis. And if we assume that the system coefficients or the expansion coefficients Z in the reduced basis, their evolution is governed by a simple system of ODEs given by this, where F is the dynamics function or the flow map. Then we can use RBF to find an approximation for F. And using this RBF approximation, we can now evolve our coefficients in time for different time steps if needed, and then again do the Galerkin projection to reconstruct our full order solutions. So using this methodology, we were able to show that even in some real world examples governed by the shallow water equations, for instance, I'm showing here a Riverine flow example in the Kissimmee River in Florida, where the original high fidelity system has about 250,000 degrees of freedom. We use a variable time step for the simulation, which runs for about 5 days, or which covers about 5 days of real-world time. And using a POD basis that offers about 0.26% reduction, we were able to show here, as is shown in the figure, which is the root mean square errors. The red plots, the red curves are the non-intrusive reduced order model using RBF, and the blue curves are the POD projection, the Riverine projection using the full POD basis. So you can see the accuracy is pretty comparable to the benchmark that we can achieve in this case, but we are able to achieve 23 times speed up with the non-intrusive model compared to the high fidelity model. And this again can be improved a little bit, and we were looking at ways to do that by finding an optimal distribution of the RBF interpolation centers. So we looked at the RBF, the theory behind radial basis function interpolations, and there are interpolation error estimates that we can leverage to propose this power scale residual greedy algorithm that we have shown that it does much better than any of the existing strategies for finding these interpolation centers in a way that now we can construct a more stable linear system for the RBF approximation, and in turn that leads to a more accurate prediction using RBFs. So the paper is, the preprint is available in arXiv, and it's still under review. So in this particular talk, we will be looking at the use of neural ODEs in this particular setting. So the reason why we were interested in this is the similarity in the frameworks that we were using for RBF and the one that we'll be using for neural ODEs. In a sense, we still do the projection to a lower dimensional space Z, and we are still trying to model our lower dimensional system using this ODE system of ODEs. But instead of using discrete hidden layers to represent our data in the lower dimensional space, the neural ODE approach tries to parameterize this derivative function using a neural network. And then using an ODE solver, we can do the forward prediction in time in the reduced space, and then iteratively solve for the neural network coefficients, for the coefficients of this neural network approximation function, in order to find a better approximation for the derivative. And then since this is a continuous representation of the evolution, this gives us the flexibility to do predictions at different points in time, and comes with certain advantages about constant memory cost and all that. So this is a figure from the original paper by Chen et al. That was published in the NeurIPS conference and was the best paper that year. So for the sake of comparison, we would compare our results with two of these classical methods. The first one is dynamic mode decomposition, which, as I was saying, is a way to find a linear approximation of a truncated Koopman operator. And the main idea here is you look at the time series of data and you split it into these two sets, which are shifted by one time snapshot. And then you try to find this transformation matrix A that relates these two splitted time series data. And this A is, you can think of as the linear reduced or linear truncated representation of your Koopman operator. So if you compute the eigen decomposition of A, using those eigenvalues and eigenvectors, you can compute your DMD modes, which is the reduced order basis for your system. And then using that reduced basis, there are analytical ways to compute your future predictions for your full order solution. This is a very elegant method that has been shown to be very successful for transient problems. On the other hand, we also will be comparing with Gaussian process regression, which is a Bayesian framework, as I said before. So instead of trying to find a continuous, deterministic continuous regression function, we'll be looking at defining a prior probability distribution with a suitable choice of kernel function. And then conditioning on the data, we'll try to determine the posterior function, the posterior distribution for that particular data. And in this way, we can find a whole family of functions that admit candidates that regress in the data. So quickly, I will be looking at two types of examples or numerical examples. One is a very famous benchmark problem using 2D incompressible Navier-Stokes equations of flow around a cylinder. This has been solved in OpenFOAM, where every variable, there are three variables, U, V, and P, and pressure. Every variable has about 14,000 computational degrees of freedom. The simulation runs for 6 seconds, but for the training, we'll be using the time period from 2.5 to about 5 seconds with a training time step, which is coarser. And then we'll compute using the reduced order model, we'll compute solutions from 2.5 to 6 seconds, which is a little bit longer than the training period. And we'll also use a finite time step just to see the interpolation quality. Using the inferences that we draw from the performance of our methods on this example, we'll try to now extend our application to the full 2D depth average shallow water equations, which is a workhorse for riverine flow, coastal flow, nearshore flow problems. And in the Army Corps of Engineers, we have an in-house open source code called the Adaptive Hydraulics, which is a fully adaptive continuous Gilbertian finite element engine that uses SUPG stabilization for solving shallow water equation type systems. So let's jump into the results with the Navier-Stokes equations first. So here I'm showing what we have. I've tried to compile some results that we were able to achieve with our neural ODE architectures. So we compared about 400 different architectures and hyperparameter configurations for doing this problem. So for instance, we looked at different solvers, different ODE solvers. We looked at different optimizers. We looked at different types of scaling of the input data and different learning rate scheduling functions as well. And obviously then we also were looking at different ways to construct a network. So different layers, different units per layer, different activation functions. We also experimented with the use of augmented neural ODEs. And these represent the sort of the 8 best neural networks that we were able to generate for training on this data. As you can see, the mean square errors that we obtain for these networks are pretty much on the same level of accuracy. One thing to note is the training time that we need for these kinds of networks. So using these 8 best models, as I might say, here I'm showing the comparison of the prediction on the expansion coefficients in the reduced space. So there is the true solution, which we have generated using OpenFOAM, and then we project that true solution onto the reduced space. And then we also compare that with all the predictions obtained with these different neural ODE models. And in the eyeball norm, you can see that they're all pretty much the same in terms of accuracy. Some observations, we noticed that scaling is a very important factor, as is quite commonly known for machine learning algorithms. So for instance, if we use tan-H activation functions, we require the input states to be scaled from -1 to +1 for each component. Whereas if you use something like ELU or linear activation functions, then scaling actually worsens the result. So this is the predicted solutions using the neural ODE trained model. So on the left-hand side, we have the DMD solution, the dynamic mode decomposition solution. And the second row is the neural ODE solution. And the third row is the POD reconstruction solution. So there is no learning that is used here in the latent space. This is just reconstruction error. So again, in the eyeball norm, you can see that this actually seems to capture all the vortex dynamics or the vortex shedding dynamics of the flow very well, each of these methods. And on the right-hand column, we have the errors for each of these methods. Again, it's quite clear that DMD produces a much more accurate solution than the other two. But what is interesting is that this POD reconstruction error is in a sense the best that the neural ODE model can do. And it seems like it's able to actually capture that POD the POD solution pretty well in terms of accuracy. And the next slide will be clear why the DMD method actually seems to do even better than that. Excuse me. So here, I'm actually showing comparison between 2 different realizations of the DMD method and 2 of the best neural ODE architectures. And this is the root mean square errors of prediction. So again, going back to the fact that the DMD was actually seemed to be doing better than the neural ODE and the POD methods. This is because of the fact that here we are using a much more finer, much more richer basis size for the DMD method. That's the result that we were showing before. So when we use that richer basis size, you can see the DMD root mean square error is obviously by far the best compared to all the other methods. But in order to actually make a more fair comparison, we also ran tests with a coarser basis for the DMD, which is more in parity with the neural ODE models. And for that particular DMD realization, you can see that now the error actually goes up. It becomes worse than the neural ODE root mean square errors. Another thing to notice here is that the POD reconstruction root mean square error is also present in here, which is almost indistinguishable from the neural ODE models for the pressure solution. And here also it's on the same order of magnitude for the X velocity solution. And the vertical line here shows that this is the training window. 2.5 to 5 seconds is where we are predicting with a finer time step, but inside the training window. Whereas here, the error that we're seeing here, this is actually extrapolation, where we didn't have any training data that the neural ODE model was using. And it seems to do pretty well even going outside the training window. So now, using this insight, let's move on to the shallow water examples. We have on the left one particular case of tidal flow in the San Diego Bay, where the original high dimensional model has about 6,000 computational degrees of freedom per variable. The original simulator runs for 50 hours with and we use about 100 seconds as our training time step, and we do our predictions on 50 seconds. This shows the tidal inflow forcing data that we're applying to the model, and the vertical red lines shows the actual training window that we're using for our ROM calculations. The right column is a riverine flow in Red River, which is somewhere a section of the Red River, which is in lower Louisiana. And here again, each variable has about 12,000 computational degrees of freedom. The training time step is 90 seconds and the computational testing time step is 30 seconds. This here shows the hydrograph inflow and tailwater elevation data that we are enforcing or imposing on our computation model. And the vertical lines show the actual training window. So as you can see, there are some interesting artifacts with respect to localized flow features, helical flows and stuff that happen at the bends of this particular model. And that's why, because of that and because of the advective nature of the flow, this particular flow actually doesn't admit a very efficient reduction in terms of the POD basis, because it has a very large Kolmogorov width. So first, looking at the San Diego Bay results, we have compared with a radial basis function method, the DMD, Gaussian process regression, and neural ODEs. And in order to sort of see the best of each world, we tried to have different levels of resolution that we are allowing each method to take. For instance, this is the number of reduced basis degrees of freedoms for each method, which obviously allows for different reduction ratios. And also, we actually use a finer time step of training data for RBF, DMD, and neural ODE method versus what we require to use for the Gaussian process regression method. So here, let's look at the root mean square errors again. Obviously, with DMD, when we use the finer reduced basis, the root mean square error is obviously uniformly better than most of the methods. With the RBF, we see a certain artifact, which is an accumulation of error with time. And this is in part due to the way we actually discretize our ODE system, our reduced ODE system in time, which is just using a basic forward Euler discretization. And we have some recent work where we actually use higher order discretization, and this reduces this accumulation of error drastically, makes it much more tractable. The GPR method obviously does pretty well, even with this coarser training data, but there is also some variability that is added to this method, and this is something that I'm going to discuss in the next slide. And the other thing to note is that the neural ODE method, though not as accurate as all the other methods, it's still doing fairly well and is very stable in terms of prediction accuracy over time. So this is, again, the comparison of the coefficients in the POD projection space. For instance, I'm showing here for X velocity, the most dominant mode, the second mode, and the third mode. And then again, for depth, the most dominant, the second and third modes, with all the different methods. As you can see, for the dominant modes, almost each of the methods do very, very well. And this is the reason behind the variability in the GPR predictions is as soon as we start going into some of the lower, less dominant modes, which have much lower scales of variation, unless you're very, very careful in choosing the regularization of your GPR kernel, there might be a little bit of uncertainty that is left in the prediction of these modes, and that kind of causes the additional variability in your predictions. So as a remedy, we have looked at either using variable regularizations of different modes or looking at composite kernels, which is a combination of different types of GPR kernels that we can use to remedy this problem. And it seems the results are much promising in that way. And this is finally full field solutions using each of those methods. As you can see in the eyeball norm, the top row, which represents the actual solution profiles, are all pretty similar. This is RBF, this is DMD, this is GPR, and this is node. And this is the time snapshot is at 45 hours, which is almost towards the end of the simulation period. But if you look at the actual error profiles, obviously the error range is the lowest with GPR and DMD. And even though the error range is kind of similar with node and RBF, you can see that the node errors are much more localized as opposed to a more uniform distribution of error with RBF. So this is something that encourages us to think that we can actually figure out ways to make make the node approximation even better by maybe enriching the POD basis that is being used or looking at some other methods. Now, finally, to look at the Red River prediction results. What we did here is we wanted to look at a few different things. First of all, as I said, the Kolmogorov width being very large, we need a large number of degrees of freedom for expressing our POD basis, which is what we allowed our RBF approximation to use. The GPR is a little bit more flexible in this regard and even uses coarser training data as we've seen before. But we wanted to see how well the neural ODE method does, even when we do not use a very fine reduced basis, just because of the fact that the neural ODE training itself is so expensive. If we are to work with a smaller system, can we still hope to get a good result, a good approximation in that sense? And then we also looked at two different resolutions of the DMD basis to do these projections. So this first figure is a much more coarser much more coarser basis for the DMD, and you can see obviously the DMD predictions are the worst, whereas almost all the other methods kind of maintain their previous characteristics. There is some accumulation of error with RBF. The node actually does pretty well. It remains within about 5% error over the time, even while it's using such a the coarsest, I would say, POD basis. And then the next figure here is where we are allowing the DMD method to use a much finer representation in the reduced space. And then, as usual, as expected, the DMD error drops below everyone else. Whereas the others, I mean, it's the same model that we're using for the others here. So now, again, looking at the expansion coefficients, this is with the coarser degrees of freedom for DMD. You can see that, again, the representation error is absolutely terrible, even in the most dominant modes. And this also ties to the fact that DMD doesn't necessarily use the energetic criteria in selection of modes. So the frequencies that are being selected inside these 30 degrees of freedom may not correspond directly to the most energetic modes. So it's not necessarily representing this particular mode well. Another thing to notice here is you can see the node predictions have no dynamics, and as soon as you look at the higher modes for depth. And this is because of the fact that we were forcing our node model to use a much coarser representation of the POD basis. So there is only one degree of freedom in the depth variable that we're training our node model on, and that is actually enough, because you can see this difference in scale in the depth variable going down from about 2 orders of magnitude between the two different modes. And then this is similarly the expansion coefficient comparison with the finer degrees of freedom using in DMD, and you can see automatically the errors actually reduce much drastically as soon as you allow the DMD method to use a finer basis. And then finally, for the full order solutions, We look at an intermediate time, which is 5 hours. Again, the left column is RBF. This is TMD solution. This is GPR, and this is node. The errors are pretty much what we have noticed before in terms of different, in terms of the characteristics of each method. But we still see the same thing where the localized errors are, or at least the node predictions actually give you localized errors as opposed to a more generic uniform error profile for RBF, which in this particular case means that we are definitely, we found this later as well, like if we use a more finer basis for our node model to construct our node model, which captures the stress profiles that are in these local flow features, then these errors reduce drastically as well. So this is a summary of our findings. The main ideas being that we are looking at all these different methods with a future, with a sense of future work of extending everything to a more parametric setup. And for some of these methods, for instance, GPR, there is actually a very elegant tensor decomposition based approach that was introduced by Professor Hestaton and his colleagues 2 years ago, which is something that we have found very useful as well. And then for other methods, there are certain variants that are available as well, and we are developing on those. The main takeaway from the neural ODE approach was we need to look at different implementational frameworks in order to drastically reduce the training times of these neural ODEs, so that we can also do a better hyperparameter search and figure out more optimal models. With that, I'd like to end here. Our code for generating the results of all these papers is available publicly in this particular link. These are the 2 of the papers that we have cited for our previous work. And this is my contact information, so I'd be happy to take any questions if there are. Thank you.
Thanks, sir. We have time for maybe a couple questions or one question before the break. So Carlos asks, how to use the neural ODE? You provide the initial temporal coefficient for each mode and forecast the rest of the sequence, or do you split into smaller sequences?
So given the nature of our data, we haven't needed to split into smaller sequences. We provide the initial temporal coefficient to the ODE solver, and then the way, so one thing which I didn't mention was all the neural ODE work was done using the TensorFlow implementation called TF-diffiq. So under the hood of that implementation, the ODE solver spits out the intermediate predictions that it gets during the time interval. And because we have data of that, the loss function actually takes into account all those discrepancies while calculating the loss as well. So that's the approach we have used without actually implementing mini batches to split our time series. But that's something that we need to do as well. The most standard mini batch approach is something that doesn't work very well, we have found out. So we need to figure out a better way to integrate mini batches as well as optimization while using mini batches, so that it does better in terms of actual model performance.
And Carlos would like to follow up with, how do you regularize the model?
Are you talking about the neural ODE model? So I mean,
yes, yeah, he's asking how do you?
Yeah. So we don't necessarily need to actually have regularization of the neural ODE model, in the sense that as long as we have a good representation of the dynamics of the system in our original snapshot space, then just by using normalization of the data, we are able to, the ODE solver is actually able to capture the dynamics very well. That's what we have found. But other than that, unlike some of the other neural network or machine learning approaches, we haven't necessarily seen the need of regularization. So one thing that might be interesting here is the augmented neural ODE approach is somewhat of a way of looking at regularization of neural ODEs. In our particular examples, we found that using augmented nodes doesn't necessarily give any benefits to the learning of our method.